Our task will be to find the equivalent resistance of this network at the terminals A, B. At first glance, this resistor ladder network may seem a complicated task, but it's just a combination of series and parallel resistors connected together. Starting from the right-hand side and using the simplified equation for two parallel resistors, we can find the equivalent resistance of R8 and R10 combination and call it RA, which can be replaced by one resistor, which is equal to R8 in series with R10, which are in parallel with R9. That means that RA is equal to R9 times the quantity R8 plus R10 divided by the sum of R9 plus R8 plus R10, or 6 times the quantity 10 plus 2 divided by the sum of 6 plus 10 plus 2, or 4 ohms. Now, RA is in series with R7, therefore the total resistance will be RA plus R7, which is 4 plus 8, or 12 ohms. This resistive value of 12 ohms is now in parallel with R6 and can be calculated as RB, which is calculated similarly to the previous calculation. 6 times the quantity 4 plus 8 divided by 6 plus 4 plus 8, which is equal to 4 ohms. The resistor RB is in series with R5. Therefore, the total resistance will be RB plus R5, which is equal to 4 plus 4, which is equal to 8 ohms, as shown here. This resistive value of 8 ohms is now in parallel with R4 and can be calculated as RC, as shown, and equal to 4 ohms. RC is in series with R3, therefore the total resistance will be RC plus R3, which is equal to 8 ohms, as shown. This resistive value of 8 ohms is now in parallel with R2, from which we can calculate RD as 4 ohms. RD is in series with R1, and therefore the total resistance will be RD plus R1, or 4 plus 6, which is equal to 10 ohms, as shown. When a combination resistive network such as this, comprising of 10 individual resistors connected together in series and parallel combinations, they can be replaced with just one single equivalent circuit, REQ, of a value of 10 ohms. When solving any combinational resistor circuit that is made up of resistors in series and parallel branches, the first step we need to take is to identify the simple series and parallel resistor branches and replace them with equivalent resistors. This step will allow us to reduce the complexity of the circuit and help us to transform a complex combinational resistive circuit into a single equivalent resistance, remembering that series circuits are voltage dividers and parallel circuits are current dividers, subsequently allowing us to calculate all the currents and voltage drops in each of the branches. This brings us to the end of practice problem number 3. If you want to look at the full range of practice problems, I have them on my Stan store at https://stan.store/GVB.